Our last speaker of this morning session is Bingxue Tao from Kyoto University, who's going to tell us about the extension problem of quasimorphisms. Whenever you're ready, Bingxue.
Okay, thanks for introduction. So today I will talk about the extension problem of quasimorphisms. First, let me introduce what is quasimorphism. So let G be a group, and so a function on G is called a quasimorphism if its defect defined by the following is finite. So here you could see that a homomorphism is obviously a quasimorphism because the right-hand side is vanishes, and a bounded function is also a quasimorphism because here every value of phi is bounded, so the right-hand side is bounded. So we say that a trivial quasimorphism is a sum of a homomorphism and bounded functions. And this is our notation that we use as hat QG to denote all quasimorphisms on G. And there is a classical result that is not hard to check, is that the quotient of this hat QG by trivial quasimorphisms is isomorphic to the kernel of the comparison map from the bounded cohomology to the to the group cohomology of G. And this is also one of the reasons why quasimorphisms are important. If you can find a non-trivial quasimorphism on the group G, then you could say that the bounded cohomology of G is non-trivial. So, but for many groups, for example, amenable groups, the second bounded cohomology vanishes. And in particular, we also know that any quasimorphisms on G is trivial. So, so next I will give you an example which constructs non-trivial quasimorphism. So here is a classical example constructed by Brooks in 1981 for free groups. Here, let F be a free group on a symmetric generating set S, and W be a reduced word on S. So you can take any reduced word you like and define a counting function, which is this CWG is to count the maximum number of disjoint copies of W in the reduced representative of G. So for example, if you take W to be the word AB, and you take G to be ABABA, and then you know that this CWG is equal to 2. So now we can define a counting quasimorphism on this group F to be the CWG minus CW inverse G. And we can show that if the word length of W is at least 2, then HW is a non-trivial quasimorphism with a defect at most 2. And since there are many reduced words on S on this generating set, you can prove that there are many independent non-trivial quasimorphisms. And this construction for free groups has already been generalized to hyperbolic groups and mapping class groups of surfaces and more groups with some hyperbolic features. So yeah, hyperbolic groups are by Epstein Fujiwara, and mapping class groups are by Festelina Fujiwara. So as I said, there are many counting. If you find one counting quasimorphism on the free group, then there are many. Well, there are many counting quasimorphisms on the free groups, also on this on hyperbolic groups and mapping class groups. So the second boundary cohomology is infinite dimensional. And you could say that this if you restrict this HW on the cyclic subgroup generated by W, this HW is just a homomorphism. And so from the point of view of extension of quasimorphism, you can say that this HW is an extension of the obvious homomorphism from W to the power n to n. So let me state the extension problem of quasimorphism and give you some simple necessary condition. Okay. So you have a group G and a subgroup K. The question is simply under what conditions can a quasimorphism on K be extended to a quasimorphism on G? Here we say extended. Here we say this quasimorphism extends to a quasimorphism on the whole group, where we mean that it is a strict extension. So if you have a quasimorphism on K, and you ask does there exist a quasimorphism on G such that the restriction is just fine. And first we give we introduce a definition about G quasi-invariant quasimorphism. A quasimorphism on K is called G quasi-invariant if for any two elements in K that are conjugate in G, the value of phi should be uniformly bounded. So why we care about this kind of quasimorphism? Because it is easy to see that G quasi-invariant is always necessary for extendability. So by definition of quasimorphisms, you can estimate that you have this inequality. So first you can decompose this. Here we use 2d5, and then we use another 1d5 to get this inequality. But what do we need in addition? And from the previous results, like counting quasimorphisms, we have an intuition that some sort of relative hyperbolicity may be useful. Because on those groups we use some sort of hyperbolicity. Because for mapping class group, you need to act the mapping class group on the curve graph. and to study the quasimorphisms. And here, this curve graph is hyperbolic. So we always need some hyperbolicity. So first, let me introduce the weakest relative hyperbolicity, which is just to define G is weakly hyperbolic relative to a subgroup K and a relative generating set if this KD graph is hyperbolic. However, this notion is too weak to derive something useful, even if we require this relative generating set to be finite. So we need some we need to add some condition. To state the next condition of relative hyperbolicity, we need let's first go to the relative group presentations, and we will use the group presentations to give the definition. So a relative presentation of a group with respect to a subgroup and a subset of the relative generating set is in this form. So the generating set is K and is a union of K and X, and the relations contains all relations of K, and R is a rest relations. So, well, here all relations of K means that you can take it to be any to be any word like this, which is which equals to 1, which equals to the identity in G. And a relative isoperimetric function with respect to this relative presentation is function f, such that for every n and every word w on x, I'm sorry, here should be the every word on the union of x and k is length at most n, and sets such that w represents the identity in G. There is a decomposition of w into a product of the conjugates of relators. So this equality holds in this free product. Here, fx means the free group with the basis x. And why it is called isoperimetric function is because we always have that this k is at most fn. So we use fn to control the length of this decomposition. And a third definition is that we say the relative representation of G is bounded if all elements from R have uniformly bounded word lengths. Okay, let me introduce this stronger relative hyperbolicity. That is hyperbolically embedded subgroups. So first, the weak relative hyperbolicity we introduced before is proved to be equivalent to the right-hand side. So there exists a bounded relative presentation with a linear relative hyperbolicity function. And from this, we can add some conditions, which is if moreover there are only finitely many k that appear in relators in R, then we say that this subgroup is hyperbolically embedded. So here is a theorem by Damani, Girardo, and Olsen. So it's cylindrically hyperbolic group. So I didn't introduce what is cylindrically hyperbolic groups, but I will say something about it. And so every cylindrically hyperbolic group contains a hyperbolically embedded subgroup, which is free product, which is a free group, and a direct product with this finite group. And so this cylindrically hyperbolic group is a very weak, or say, a generalization of hyperbolic groups, which contains like mapping class group, automorphism groups of the free groups, and many groups. And so the first result I want to introduce is about extendability from hyperbolically embedded subgroups. So we say a quasimorphism is antisymmetric just to say the value on G inverse is minus by T. So the theorem by Hull-Osin states that if K is a hyperbolically embedded subgroup of G, then any antisymmetric quasimorphism on K extends to G. So it is a direct corollary that if G is cylindrically hyperbolic, then there are many quasimorphisms on G because we can choose K to be a virtually free subgroup. But this corollary is not originally proved by Hull and Olsen. It can also be proved from the Bestovina Fujiwara. And we mentioned about G quasi-invariant. So here we didn't mention G quasi-invariant in this theorem because it is automatically satisfied on the hyperbolically embedded subgroup, since the intersection of K and its conjugate is finite for any hyperbolically embedded subgroup. And in the paper of Hull and Olsen, they also consider one classical cycles with general coefficients. And later, their results has been generalized to higher dimensional classical cycles. And this is used to show that the third bounded cohomology of eccentrically hyperbolic groups are infinite dimensional. And recently, Carstenholtz proved that the fourth bounded cohomology of free groups is non-trivial. So by the results of Fournier-Facio and Sisto, we also know that the fourth bounded cohomology of eccentrically hyperbolic groups are non-trivial. but one problem about this theorem is that any infinite normal subgroup can never be hyperbolically embedded. So their results didn't tell us anything about extension from infinite normal subgroup. So this could be seen from here. So the intersection of K and its conjugate is always fine. So how about normal subgroup? So first we want to introduce this. Give you some let's start from the central extensions. So let this be a central extension, and we can define a cocycle on G omega, and to be just SG1 SG2 and SG1 G2 inverse. Here S is any set theoretic section from G to E. And we can define two co-class in this in the second cohomology of G. This co-class does not depend on the choice of sections. So it is well defined, and it's called the Euler class of this central extension. We say that this central extension is bounded if its Euler class is represented by a bounded to cocycle. And here is a lemma to say that the boundedness of central extension is also some sort of extension problem of quasimorphism. So the central extension is bounded if and only if the identity map on Z can be extended to a quasimorphism on E. This may be known before, but it is stated in this form recently, I think. Okay, so let me give you some examples of central extension. Let's sigma be a finite type surface with a boundary component, just like this. And let this hat sigma to be a surface that capping this boundary into a puncture. Okay. And then there is a central extension for the capping sequence. Here T gamma is a den twist around gamma, and I think and this T gamma is the center of this mapping gas group. So classical result says that the capping sequence has a bounded Euler class. And now we want to consider some, we want to construct more central extensions. So we use this, use a pseudo-Anosov element of sigma, and let n be the normal closure of this, of a large power of n, and we take the quotient. So here, for the quotient group, here, we know that its further quotient by pi n is hierarchically hyperbolic. I don't introduce what is hyperbolically embedded, but Giorgio mentioned it in his talk, And so question is that is the quotient group of the mapping class group of sigma is also hierarchically hyperbolic. Equivalently, is this quotient a quotient extension bounded? So here is a general result says that it's also by Fournier-Facio and Mangioni and Sisto. They prove that if the central extension, original central extension is bounded, and then the quotient central extension is bounded if and only if certain quasimorphism on pi n extends to G. So this is also a extension problem of quasimorphisms. Okay. Oh, let me. So the time is limited. So let me state the main result. Let G be a group and K a subgroup, and phi is a quasimorphism. Then we can define a natural pullback of phi to the free product of K and Fx. And then let's this theta to be the natural quotient map from the free product to G. Then we define this quasimorphism to be cyclically sublinear if there exists a constant C0 such that the pullback of phi, the value of the pullback of phi on A is sublinear with respect to this. It is equivalent to say that it is sublinear with respect to the word norm of A. But here we write this X, but it doesn't matter if you consider it as a norm. So the main result is that if the group G is weakly hyperbolically relative to K and X, then any cyclically sublinear quasimorphism on K extends to G. Okay. Finally, let me mention some corollary of this main result. So back to the Hull-Osin setting, if K is hyperbolically embedded, then any quasimorphism on K extends to G. This result slightly generalizes Hull-Osin's result because they require antisymmetricity. And our proof is much simpler. The second corollary says that if K is a normal subgroup and the quotient group is hyperbolic, then any G quasi-invariant quasimorphism extends to G. And the third corollary is that if if G is a pseudo-Anosov mapping class on a surface, and we take the quotient of this mapping class group by the normal closure of G to the power of n, then any G quasi-invariant quasimorphism extends to the mapping class group. And this gives an affirmative answer to the question asked by Fournier-Facio, Mangioni, and Sisto. So ask P.